Okay, so this material is taken from periandata.com, and title of this presentation is about Introduction to Linear Regression. So if you have some questions, you can type in your questions in our inbox, and or you can use your microphone to speak up. Okay, so the introduction to linear regression advises us to read the chapters 2 and 3 of the book Introduction to Statistical Learning by Garrett James, to be able to understand the mathematical concept behind linear regression. As you have maybe discussed this or learned this from your previous mathematics courses, the linear regression is very important also in machine learning, and you will understand that later. Okay, now in terms of the history of the linear regression, it started in 1800s, so it's pretty much very old concept. And there's a guy named Francis Galton. He was studying the relationship between parents and their children, and in particular he investigated the relationship between the heights of the fathers and their sons. So from his investigation, he discovered that a man's son tended to be roughly as tall as his father. However, Galton's breakthrough was that the son's height tended to be closer. So this is his general conclusion. The son's height tended to be closer to the overall average height of all people. Okay, so in an example given, for example, Shaquille O'Neal. We all know that Shaquille O'Neal is a retired NBA player. He is really tall, 7 feet and 1 inch. That's around 2.2 meters. So it says that if Shaq has a son, and I believe that Shaq has a son, and he has also a daughter, chances are they will be pretty tall too. However, Shaq is such an anomaly that there is also a very good chance that his son will not be as tall as Shaq or Shaquille O'Neal. Okay? So it turns out this is the case, no? So the son of Shaq is also a tall guy, but not as tall as him, no? It's around 6 feet and 7 inches. So it's around maybe around 4 inches shorter than his father. Galton called this phenomenon regression. Okay? As in, a father-son's height tends to regress or drift towards the mean average height. So from this we can draw some explanation about what a regression is. Okay? So let's take the simplest possible example, calculating a regression with only 2 data points. Now, from the illustration here, you will see that there are 2 points. No? We have from the x-axis we have from 1.5 to 5.5 points, and from the y-axis we can see from 1.5 we have from 3 up to 11 points. And the 2 points that are displayed here are in the coordinates of 2 and 4, and the other one is 5 and 10. Okay? So if we try to all we're trying to do here is, when we calculate our regression line, so all we have to do is to draw a line that's as close as to every dot as possible. No? Of course, if we draw a line using 2 points, we can draw a straight line. Okay? But what if there are many points? We can still draw a straight line connecting 2 points. And what about the other dots? Okay, so for classic linear regression or least square methods, what we do is to measure the closeness in the up and down direction. As an example, okay, the concept of that, we can apply it to graph with more than just 2 data points. So actually, we can make a straight line here, but we will have to measure the distances of the other points, the regression line that we have made. So by doing this, we could take, for example, multiple men and their sons' heights and do things like tell a man how tall we expect his son to be before he even has a son. Okay? So that will be the conclusion. Now, our goal with linear regression is to minimize the vertical distance between all the data points and our line. So if our line here is the line, this one colored red, okay, the goal is to minimize the vertical distance. So when we say vertical distance, we're talking about the distance of every point from our regression line, and we will measure the vertical distance. For example, if this point, we measure the vertical distance from our line. So if we want to determine the best line, we are actually attempting to minimize the distance between all the points. So we're considering all the points. So we will not just create a regression line for the sake of a line or for the sake of drawing a certain regression line. But we are actually drawing a line that will determine, to attempt to minimize the distance between all the points, okay, and their distance to our regression line. Okay, so we can draw a line somewhere here, but that will be too far from here, from the above points. We can draw a line from here, but that would be too far from the points below. So we put the line in the middle so that it will be minimizing the distance from the top points, okay, and the below points. So that will be the case, okay. Now there are lots of different ways to minimize the distance between all the points to our regression line, and some of the methods that can be used are sum of squared errors, sum of absolute errors, etc. But all these methods have a general goal of minimizing this distance. Okay? For example, one of the most popular methods is the least square methods. So here we have blue data points along our x and y axis. Okay? So we want to fit a linear regression line here. Now, considering the different points, now we have 5 points here. The question is, how do we decide which line is the best fitting one? So what we do is to use the least square method, which is fitted by minimizing the sum of the squares of the residuals. So the residuals is the difference between the observation, the y value and the fitted line. So you can see that the residual here is the difference of the point from our regression line. So that is colored in red. So that will be considered as the residual. Okay? So we'll try to give some example of that later. Okay? We'll give some example of the regression, linear regression. But before we proceed with that, let me discuss first the other topic, which is logistic regression. Okay? So for the logistic regression, so here's our topic for that. So we are advised to also read the mathematical concept behind logistic regression in sections 4 to 4.3 of Introduction to Statistical Learning by Garrett James. Okay. So for example, we want to actually the linear regression is somehow related to predicting the possible points, no, that would be the possible points that would be associated with our linear regression. But in logistic regression, we use it for classifications, no. So classification is different from prediction, and there are many types of examples of classification problems, such as, for example, we can detect whether an email is a spam or not a spam, okay? And we can also diagnose diseases, whether it is an exact for example, is it a cancer or not, or is it malignant or not. So most probably in those cases, logistic regression is used. So these are all example of what we call binary classification, wherein, no, from the word itself, binary, we have only two classifications, whether it is true or false, whether it is yes or no, okay, whether it is a spam or not. Okay, so that is what we call the binary classification. We have to classify our data set, for example, whether it is applicable for a certain case, such as the following examples here. Okay, so in our regression problem, we try to predict a continuous value, no, continuous value in our regression, in our linear regression. For example, we can detect a certain price of a product, what will be the next price next month. Okay, so what will be the price, what will be the increase in the price of a certain product, no? So we can detect that, or we can predict that using regression or linear regression. So although it says here that the name may be confusing, logistic regression allows us to solve classification problems, no? Not prediction. So classification problems where we are trying to predict discrete categories. And the convention for binary classification, as I have said earlier, we will only have two classes, no? It's either 0 or 1. It can be a ham or a spam, or it can be a disease or not a disease. Okay? So actually, we cannot use a normal linear regression model on binary groups. So considering this image here, so on the y-axis we have the probability, and we have some points here, and as you can see, we have drawn a linear regression line here, but the classification between 1 and 0 is very far, and there are also lots of points scattered below 0. So that this will not be a good fit when we try to classify using a linear regression line. So therefore, in classifying whether it is 1 or 0, we cannot use linear regression for our model. Okay, so instead, what we have to do, we can transform our linear regression to a logistic regression curve. Now, as you can see from here, the linear regression line was converted or transformed into a logistic regression curve, where the classification of 1 to 0 can be distinguished. Okay? And how do we do that? No? We can convert a linear regression line to logistic regression using the sigmoid function, no? So the sigmoid function is also known as the logistic function, wherein it takes in any value and outputs it to be between 0 and 1. So this is the formula that can be used. So the sigmoid function of C can be equal to 1 over 1 plus e raised to negative c. Okay? So this means we can take our linear regression solution and place it into the sigmoid function. So how do we do that? So this is an example, no? So if we have the linear model as y is equal to b of 0 and b of 1 multiplied by x, so that will be our linear model, we can convert that to our logistic model using the formula P is equal to 1 over 1 plus. So the formula here, the z, you know, the function of z will be used. We will take the linear model and replace it in our negative exponent of the function of z. So that will be how we can translate our linear model into logistic model. So what will it produce us, no? This will result in a probability from 0 to 1, no, belonging in the 1 class. So you will also notice that in sigmoid function we can set a cutoff point of 0.5, no? So as we can see from here, there's a line drawn here. This is what we call the cutoff point. So that anything below it will be categorized as class 0, and above the cutoff point we can categorize it as class 1. Okay, so therefore, for example, if you have some points here and the point is above 0.5, those will be class 1, and the other one, if they are below the cutoff points, so therefore there can be categorized as class 0. Okay, so we use the logistic function actually to output a value ranging from 0 to 1. Based off of this probability, we can now assign a class, whether, for example, if all those points are located here above our sometimes we call it the threshold, okay, the cutoff point, for example. So that can be a spam or not. Okay, so we can categorize this as a spam, or is it a disease, and the other one is the opposite of that, no? It can either not a spam or not a disease. Okay, now after we train a logistic regression model on some training data, we can also evaluate the performance on some test data. So we can use a confusion matrix to evaluate the classification models, no? So from our module 1, we discuss the confusion matrix to evaluate our model, no? For example, let's imagine testing for disease, no, and the number of samples will be equal to 165, and the predicted no is 50, and the actual no is 50, and the predicted yes is 10. Okay, so we can actually take the no as our false values, or 0, class 0, and the yes could be our true values, or class 1. Okay, so we can now compute for how many true positives, true negatives, false positives, and false negatives. Okay, for the accuracy, we can compute using the formula the sum of the true positives plus the sum of the true negatives. So if these are the true positives, okay, and these are the true negatives, so we can actually compute it as 150 divided by the total, which is 165. So that's around 91%. So that will be actually the overall accuracy of the model in this case. Okay? For the error rate, we can actually use the opposite. Okay? By using the false positives plus the false negatives, or we can just subtract this by 1, no? 1 minus 0.91, that will be equal to 0.09. Okay? Because the error rate will always be the opposite of the accuracy rate. So this is an example of the result. So whether we can actually, when we say some errors are done, no, in our prediction or classification, so you can see this man was diagnosed to be pregnant, but actually it can be, no, but the data insists that this man is pregnant, no, so that will be an error. So we call it a type 1 error called false positive. Okay, and another one, this lady is definitely, obviously she's pregnant, but the doctor says, or the machine learning tells us that she's not pregnant. So that will be considered as type 2 error or false negative. So we'll have some example of this later, this logistic regression, and as well as the linear regression. Okay, so for now I'm going to show you, let me open my Jupyter notebook. Okay, and let me share to you my for a while I just will open I will just open a, let me open this one. Okay, so let me share this to you, this page. So you can also follow me if you want, no? You can open your Jupyter notebook and follow me as I am going to give you an example of a linear regression. And I will also give you, I will send you the I will send you the data, for our for our example. Okay, so in this example, so let me just put it as a markdown. Okay, so let's say we have linear regression. Okay, so linear regression example. So let's have this example. So the data set that we're going to use is the data set that we're going to use is the USA housing, no, .csv. So I will mark it as a markdown because I'm just doing some preparations for this one, no? So do you have this do you have this data set yet? So if not, so I guess I'm going to send you the data set. So let me just find it. So I think it's in here. Okay, the USA housing. So yeah, so I'm going to send to your inbox. And you will receive the dataset, and you can download the dataset so that you can also follow. Okay, so USA housing dataset. Let me just copy the or upload the dataset for you. Okay, so it's already sent, okay? Okay, so while you are downloading the file, no, you can now check your files in your inbox. So while you're downloading the file, so let's first examine what we're trying to accomplish this morning. No? So actually, I'm going to demonstrate how we can use linear regression. No? So actually, the codes that you will see here, this is just for reference. No? Let's say, for example, in this data set, actually it contains many information. No? This data set, although it's a small data set, it contains many information. No? As you can see later, no? We can check the data. So, but before we check the data, let's try to import our libraries, no, that we can use. No, of course we usually import our pandas, and we use the alias PD for better management of our codes. No, and then we also use NumPy as NP, and then for visualization we import our matplotlib .pyplot. Okay, so matplotlib .pyplot. So this will be the common thing that we can see. So we can abbreviate it as PLT. Okay, and then we can also import another visualization library, which is the Seaborn. So we can import it as SNS. Now, so that the visualization can be displayed in our notebook, so we can use percent matplotlib inline. Okay, so inline. Okay, so we can run this. Okay, so it's already run. Now we can now check our data. Okay, for the data, we can now say that as an example, we can have a data. Okay, and we can call, using pandas, we can call the we can load the data set. No? So for example, read CSV, and where is this file located? So I think the file, I'm going to copy the file, and it should be where my notebook is. No? And where is my notebook supposedly? Oh, it's in the CPE. It's in my documents, CPE 012. No, so actually this notebook is saved in a different location. So I think I made a mistake here, because I'm using the so anyway, I will just copy the data set in this location. So I already copied it, so I will just go to the and copy the data set so that it will load properly. So if you want to load your data set, make sure that your data set will be found where the location is. No, otherwise you can just write the whole directory here. Okay, the path of the directory. So also you have to take note of the spelling of your data set. No? So your data set should have the correct spelling. Okay, so this is now our data. Okay, so to be able to know whether we successfully loaded the data, so we can type data, for example, and that's the data. No? So from the data, what can we examine here? So we can examine that we have an average area income of the residents of the city. where the house is located in. So actually this is USA housing. That means we're talking about houses here, okay, and the prices of the house. So we can also see the average age of the houses, okay, the average age. Actually it's located somewhere here, okay. So the average area, the average age, and then the average number of rooms, okay, the average number of rooms in the same city, or the average number of rooms for houses, and the average number of bedrooms also, and the average, actually we can also see the area population of that city where the city house is located in. We can also see the price and the address for the house, no? So this is the address of the house. So you can see from here, so without examining the data using pandas, we can see that these are all numbers, no? And this one is an object made up of strings, and these are all numbers. So if we try to describe, okay, the information, so we can just actually use data, okay, and then we can also use info so that we can know the information of our data. So from the information of the data, we shall now know the range index from 0 to 499. So we have 5,000 entries, and we have 7 columns, and the columns are the following. So we have column 0, which is the average area income. It's a non-null count, okay. So you can see here that they are all float, no? They are all floats or fractional, with fractional numbers or decimal numbers. Only one column is categorized as object, and all of that are all floats. So we can use these numbers because they are all numbers. In machine learning, we can use numbers only to fit in a model. However, we cannot use the object to fit in a model, no? Or otherwise, we can convert the object into a number, no, if you want. Okay. Now, if you try to use the describe method, so you can see here that we have now the basic count, which is 5,000. So we have 5,000 entries, as you can see from here, and we can also see the mean or the average, no, of all the entries for the income or the house area or house area age or area house age, and the number of rooms, number of bedrooms, the population, and the price. You can also see the standard deviation and the minimum, okay, and the maximum. So that is what we can see from the data set that we have. Okay, so if you want to see the columns, for example, we don't know the columns, so you can just type data.columns. So we can now see the columns. Right? Now from here we can now actually create some visualizations, no? For example, we can use the seaborn, and we can make a pair plot. Okay, we can use a pair plot for our data. Okay, so we use the data as our parameter for the function. We are actually importing a function called pair plot from our SNS or seaborn library. Okay, so this will somehow do so depending on the speed of your computer, it will now show us the plots, no, to be able to check our data. Now, for example, in the average area income, we shall have the following pair plots, no? From the diagonal part, we will see the distribution of the data set. So you will notice here that based from here, you will notice that all of the distribution are fine, equally distributed, as denoted by the shape of the distribution. However, when we see the average number of bedrooms, it is somehow different, no? Because actually, when we talk about number of bedrooms, we will see from the idea here that the average number of bedrooms are they have different points, no, like 0.98, 0.23, 0.14, which is not actually, should not be the case, because the average number of bedrooms should be actually in a whole number, no? There is no 3.5 bedrooms or 2.5 bedrooms or 1 3/4 bedroom. Okay? We just have 1 bedroom, 2 bedroom, 3 bedroom, 4 or 5, something like that. So you can see the distribution of the bedroom is different from the other columns. But on the other pair plots, okay, you can see some good distributions, no, of the points. Okay, so if you cannot understand the pair plots, you can also make use of a heat map. We can also use the Seaborn's heat map, okay, for our data, and we can use the correlation. No, actually, we can use, let's see the correlation first of our data. Okay, so this is the correlation. So as you can see from the diagonal part, all of that is equal to 1. Okay, and we can see the heat map of this to better understand the numbers. Okay, so we can see SNN does heat map. Okay, and then we can also use the data and its correlation. Okay, so that will be the case for our heat map. Okay, so in our heat map, you can see that the middle part is strongly correlated, and the part where it is 0, somehow it is strongly suggested by the data that it's not, seems to be perfect to be fitted in our model because of the weak correlation of these particular columns. Okay, but however, in some cases, like for example, from this point, from these colors onward, actually it's from the darkest to the lightest, we can see some strong correlation points. So we can also use those points for our model. Okay, so now let's try to after the visualization process, now that we have visited our or investigated our data set, we can now actually train a linear regression model, no? So let's try to say that, let's try to train a linear regression model. Okay, so we'll now begin to train our regression model. So actually we need to first when we try to create a model, what we do is we have learned from the process that we need first to split our data into parts, no? For example, we can identify which are X and Y arrays. Okay? So, what will be our X arrays and what will be our Y array? No? Actually, we are predicting the price, so our X will become the features or the columns related to the USA housing, no? So maybe we can use from our columns. Let's try to identify our columns. So maybe we can use the average income, average house age, average number of rooms, okay, as our average number of rooms and average number of bedrooms and the area population. But definitely we cannot use the address for our X. So we can identify the X, okay, for the data. So we can use the following. So we can just copy this. Okay. We can copy this one up to here. Okay. And then we can put it here as our X arrays. Okay. So let's try. Sorry. What happened? Okay. So we should put a double bracket here. Okay. So what happened? So there is something missing here. Okay, something is missing here. Yan. This one. Yan. So okay na yan. So our X now will be, so this is now our X. We try to identify our X. It's made up of 5 columns, but still it has 5,000 rows. And for our Y, okay, let's just leave this one. For our Y, so we can have, so we will copy the data, and we can just have the price, no? So this one will be the content of our Y. Okay, Y array. So if you see the price, so these are the prices. So this is an array from 0 to 499, and these are the contents of the array. Okay, so that will be the content of our Y. Now as we have studied, now we can split the data into training set and testing set, no? For the purpose of demonstration, we will train out the model on the training set, and then we will use the test set to evaluate the model later. Okay, so let's try to use a library from sklearn model. Okay, so let's try to have a note here. So this is for the train test split. Maybe we can use this one. Okay, so we can use the library from sklearn, and we will use the model. So when you press the tab, it will automatically give you a hint of what you're supposed to code, no? So there's no need for you to type everything. And then from that model, we will import train test split. Okay. Okay. So that is what we're going to do, to import that model, no? So after we import the model, so this will be used to use the function train test split, no? So we can now identify our X train and the X test data, and as well as the Y train and the y test. Okay, and equate it using the train test split. Okay, and we will now use actually we should put this one as small letter y, because we're using, actually when we try to, in some codes that you will see, when you identify the x, it's in capital, and then the y should be in the small letter, no? So you can see the y will be small letter. So what will be the parameters here? We will use the x data set. Okay, this data set here, the x arrays, and then we will use the y. Okay, and we will now identify, so you can see from shift tab, okay, shift double tab, what are the parameters that you can place inside this, no? So actually it's not working here right now. Okay. So but actually we can identify the test size. So let's say our test size will be 40%, no? 40%. And then we can also use the random state, okay, random state of, so that we will have the same answer. Let's use 101 for example. Okay, you can also use other numbers for the random state, but definitely we will have different answer if you have different random state number. Okay, so we can now proceed with executing this. So I think there is a SK error. So y is not defined because I did not actually execute this. I just changed this, so there is an error. Right now, there's no error now. Okay. Now we can now create and train the model. So this is how we can do that. So we can create and train the model. So how do we do that? So we also use, of course we need to train it using linear regression, right? So we will now have to import linear regression from sklearn that model. Okay, model selection. Actually not that one. We can use the linear model. Okay, so we can use the linear model, and we will import the linear regression. Okay, so because we're trying to create and train the model using linear regression, so from the sklearn that linear model, we will import linear regression, and then we can set a variable. For example, we can set lm is equal to our linear regression function. Okay, so linear regression. Okay, so and then after that, ay, hindi ko pa pala naran to, sorry naman. Okay, kaya pala ayaw. Yan. Now, after that, we can fit the model, or we can train the model using the function fit. Okay, so fit, and what are we supposed to train? So we will train the x train and the, actually we have, ayan, so andito naman siya, we can choose, and then we can choose the y train. So yan na yun. Okay, so when we try to run this one, the output of this will be very fast because of the data set. It's really simple data set. So you can see here that the output is a linear regression. Okay, And actually we have fitted the model, no? This is the model that we created for our linear regression. Okay? Now, we can now evaluate the model, no? Let's try to have another note here. Model evaluation. For the model evaluation, we can use we can check the coefficients and how we can actually interpret our coefficients, no? So how do we do that? We can actually print our model's intercept, okay, and also the coefficient of our intercept. Okay, so let's evaluate the model by checking out first. First, we need to print the intercept. So let's try to print the intercept. So how do we do that? Print lm.intercept. And then there's a space here, okay? So that will be the intercept. Okay? And we can also use coefficient, no? For example, the coefficient for our data frame, for example, so we can use the data frame for our coefficient, lm.coefficient, and then we can use the columns for our x columns, okay, and we can equate this as our coefficients. So we are adding actually a data frame, and we will use the column coefficient to see the coefficients of our income, of the area of our house, the number of rooms, the number of bedrooms, and the area population. Okay, so let's see this. So there was a problem here. Okay, so what is the problem here? So lm that coefficient x columns, tama naman. Okay, let me see this one. Mali pa rin. So somewhere here we have a problem here. Coefficient df. Let's try to to check first. Okay, so it's wrong. Columns. Okay, so kulang tayo ng columns. Okay, kulang tayo ng columns. So if we want to check now the coefficient, so we will see here, this will be the output, no? So what is the meaning of this coefficient, no? Now, how do we interpret the coefficients? So that means a 1 unit increase in the average income is associated with an increase of $21 and actually 53 cents. No? So that will be the case. So that means holding all other features fixed, if we try to increase 1 unit, no, of the average area income, it will try to increase also the price of $21.52. So basically it's the same with the average house age, no, holding all other features fixed. If we try to increase the average area house age, no, it will also be associated with an increase of how many dollars is this? $164,000, 883. Okay, so that will be the case, and the same with the other columns. So that's how we can interpret the that's how we can interpret the ano the the value for the coefficient. Okay, so now let's try to create some predictions from our model, since we already fitted using linear regression. So I think we can create some predictions from our model. So let's try to do that. So let's try to have a variable called predictions. Okay, so we can equate it to the model, and then we can use predict, and what we will use for the predict is for the test data set. Okay, so X test. Okay, that will be our prediction. So this will give us that the prediction that we will create here will be placed in a variable here, no, called predictions. Okay, so let's try to run this. So you don't see any prediction yet, but actually we can plot. No, we can plot the prediction using Matlab. So we can use PLT that scatter, now using our y-test. Now this time we will use the y-test to predict, no? Since we already have the predictions here, so we can use the predictions and the y-test. Okay, so this will be the output of that. So this is the plot of the prediction, no? So definitely we have a very good prediction based on the plots. Now if we try to draw a regression line here, somewhere here, so we can definitely have, we can actually minimize the residuals, no, the distance of the points from our regression line. Okay, we can also try to check the residual histogram, no? So check the residual histogram. So how do we do that? We can use the Seaborn and then distribution plot of our y-test. So we use the y-test predictions. Okay, so let's try to do that. So that will be the prediction. Okay, so this will be the case. We can actually do some ano here, no? We can put additional features, like for example the number of bins can be equal to 50. Okay, so that the thickness of our distribution plot will be much better looking, no, rather than the other one. Okay, so you can see here that the distribution plot typically look like this, no. Now for the other evaluation metrics, so we can use, let's try to insert below. So for these are for regression evaluation metrics. So because you'll have to use this one later. Okay, wait. So what are the common evaluation metrics? We can use the mean absolute error. And then we can also use the mean squared error, or the MSE, and the root mean squared error. So these are some of uh, the mean absolute error. Actually, it's the average error. No, this is the average error. While the MSE is actually, it's MSE is more popular than MAE, no? Because MSE is getting the square of the error, no? It actually punishes the larger errors, which tend to be useful in the real world. Okay, so MSE is squaring the error, but RMSE is even more popular than MSE, because RMSE is interpretable in the Y units. Okay, and all of these loss functions, all of these are loss functions actually, no? So we are actually computing for the error, no, for the loss function, not on the accuracy. We are computing for the loss functions because we want to minimize them. Okay, so these are the things that you should understand with this, no? So ayan, so ito yung mga metrics na pwede nating gamitin. Now you can look for the formula of this, but actually there's no need to compute for the formula because the sklearn has its own metrics, no? So we can just import from sklearn. We can import the metrics. Okay, so all the metrics will be imported here. Okay, for example, we can print our MAE. So let's have this one. So what will be our MAE? So our MAE will be equal to the metrics. Now we're calling the function metrics, and then we will call the mean absolute error, no, of our y-test. So we will use the y-test and our predictions. Okay, so that will be our MAE. So that will be the MAE. Okay, so we can just copy this one. Actually, we'll not copy na lang, siguro type na lang natin yung MSE, and then we will use the same metrics, but this time we're using the mean squared error, no? So where is the mean squared error here? This one. Okay, and the same, we will use the y-test and the predictions. So y-test and the predictions. Okay, so this will be the output, no? This will be the MSE. So you will notice that MSE is larger than the MAE. Okay, now for the root mean square error, so we have RMSE. We can use the metrics that mean squared error. But actually, before we take a look on the metrics, so we will also, since we're using the square root, no, so we'll have to put a square root here, no, because MSE or RMSE is the square root of MSE. So we can just copy this. We can copy this one and put it here. Okay, and we can also get the square root of this. Okay, so let's just check the so parang kulang siya ng isang parenthesis dito. So now it's okay. So when try to square root is not defined, okay, so kulang ng numpy. So it should be from the numpy. Okay, so yan. Okay, so that will be the root mean squared error, which is the square root of this MSE. So this is much little than this one because we're taking the square root of the error. Okay? So actually, if you are following me, you are actually have done your first real machine learning, no, activity. And if you have followed me, congratulations, because you have actually have gone a step ahead of your learning in terms of machine learning. Now, actually, this data set is just a regular data set that is used for demonstration purposes, no. But if you want to use, no, if you want to use a if you want to use a data set, no, from the real world, so I guess you can use, for example, you can use the data set from sklearn. So sklearn kasi may mga data sets tayo dyan, so we can import that. For example, we can import the load Boston dataset, and then how do we import that? We can use that command, and then we can actually use Boston and then load Boston as our function, no? So from here we can now have Boston. So this is the data set for Boston, no? It's somehow more complicated than the you can make a practice out of this, no? So we can describe, let's say for example, print Boston that description. Okay, so this will be the data set, no? So we can describe the data set of the Boston library or Boston data set. This is also used for the you can see some terms here like per capita crime rate by town, proportion of residential land zone, proportion of non-retail business, and other data. Okay, other data. So from here you can also put it in a data set, no? So from here you can see Boston DF. So that is the Boston data. Just the data, no? Just the data. So if you want, you can practice for this data set and use the same method that you have learned from this example, no? So actually this is for the linear regression example. That will be the name of our topic for today. Okay? So any questions so far? Any question? Are there any questions?